All right, section 3.2. Welcome back. So your learning objectives are to interpret a regression line, calculate the equation of the least squares regression line, calculate residuals, construct and interpret residual plots, determine how well a line fits observed data, and interpret computer regression outputs. So a regression line is a line that describes how response variable y changes as an explanatory variable x changes. We often use the regression line to predict the value of y for a given value of x. The mean x and the mean y is always a point on the regression line, even if it is not a data point. So I know that x bar, y bar is always going to be on the line of best fit. So as I have my data, I will always have x bar, y bar as a point. This is a scatter plot of the change in non-exercise activity and measured fat gain after 8 weeks for 16 healthy young adults. The plot shows a moderately strong negative linear association between the non-exercise activity change and fat gain with really no outliers. The regression line predicts fat gain from change in NEA. So this line is a predictor model. It does not mean it was the actual thing that happened. It's just what we would predict from what we see. So when non-exercise activity would be 800, we could see our line predicts a fat gain of about 0.8 after 8 weeks. All right? So this is a predicting model. So in order to show that something is a predicted model, instead of doing y equals, we use this little thing called y hat. Now when you write it out, you can just do y hat when you type it up for me, or you could just do y with a little thing after it. Or if you're fancy and you want to figure out how to use the rest of the equation stuff in there, you could actually do the y hat. All right, so y hat equals a plus bx. This is actually linear. This is just my slope. And this guy's my y-intercept. This is for my regression line, which is a prediction. Okay, so y hat is the predicted value of the response variable y for a given value of the explanatory variable. You need to get this word in there when you're describing. Even when you describe in context, you need to say it's a predicted. B is the slope and y is the, or a is the y-intercept. All right, so consider the regression line from the example. Does fidgeting keep you slim? Identify the slope and y-intercept and interpret each value in context. All right, so here I can see the y-intercept is about 3.5. So it means that the non-exercise activity would give me about a fat gain of 3.5. if I had 0. Okay. Let's say we wanted to write out the equation first off. So I would first put fat gain with a hat. If you put y hat, you need to somewhere state y hat equals predicted fat gain. Again, make sure you get that word, okay? And then x is just your NEA change. It's not predicted, it's the actual amount. Okay. So we have the equation with our slope and y-intercept already given. Sorry, that was supposed to be there. Okay, now let's go and interpret the y-intercept and the slope. Okay, so we can see our slope negative 0.00344. Remember, slope is rise over run. Or you could say it's change in y over change in x, however you like to think about it. So in this case, our change of y is the change in fat gain over the change in non-exercise activity. So when I'm doing this and I find what my slope is, so it says my slope is negative 0.00. I'm running out of room. Let me come down here. Hold on. negative 0.00344, I can put it over 1. Okay? So it tells us that for each one, this is the NEA, for each one additional NEA, our body fat goes down, so this is the fat, goes down because it's negative 0.00344. So I always think it's easy if you kind of write at least this part when you go to identify the slope. It's a lot easier to write this in context. Okay? So the y-intercept here of 3.505, it's the estimated if you don't, if you have 0 NEA. Okay, so it's how much fat gain you would have if you have 0 NEA. All right, we can use the regression line to predict the response y hat for a specific value of the explanatory variable. So here, if I wanted to see from that line that we just had, we want to predict the fat gain for a person whose NEA increased by 400 calories. So we're going to use our model, and the 400 calorie is going to go in to right here. And we could see the predicted fat gain would be about 2.13. So again, this is predicted. So we predict a fat gain of 2.13 kilograms when a person with a non-exercise activity is 400 calories. All right. Data on the IQ test scores and reading test scores for a group of 5th grade students give the following regression line. Predicted reading score equals negative 33.4 plus 0.882 times their IQ score. What's the slope of this line? Interpret the value in context. What's the y-intercept? Explain why the value of this intercept is not statistically meaningful. And then C, find the predicted reading scores for 2 children with IQs of 90 and 130. So here I can see the slope is 0.882 over 1, and this is the reading score, the predicted reading score, and this is the IQ. So it tells me for every one IQ score increase, the predicted reading score goes up 0.882. The y-intercept is negative 33.4. Why is that not statistically meaningful? Because you can't have a predicted reading score that is negative. So it's not statistically meaningful because that could never happen. And find the predicted reading scores for 2 children with 90 and 130. So you're going to plug those 2 values in right here and get outputs. Of 43.98 and 81.26. Okay, so just kind of looking over this, this is actually flip-flop. For each increase in IQ, the predicted reading score will increase by the 0.882. Okay, sorry about that. All right, extrapolation, what does that mean? So when we use the regression line to predict what would happen, kind of how we plugged in just over here, we plugged in the 90 and the 130 to see what those predicted reading scores would be. So if I plug in a value that is way outside all the rest of the observed values of x, that's called extrapolation, and we don't want to ever do that. Okay, these predictions are not accurate usually. So don't make predictions using values of x that are much larger or much smaller than those that are actually appear in your data. And just don't forget the mean x and mean y is always on the regression line. All right, here's an old AP question. An experiment was conducted to study the effect of temperature on the reliability of an electronic device used in an undersea communication system. The experiment was done in a laboratory where tanks of seawater were maintained at either 10 degrees Celsius, 30 degrees Celsius, 50 degrees Celsius, or 70 degrees Celsius. After the electronic devices were submerged in the tanks for 5,000 hours, each device was inspected to determine if it was still working. The following table provides information on the number of devices tested at each temperature and the number of working devices at the end of the 5,000-hour test. All right, you may assume that the result for any single device is not influenced by the result for any other device. Using the information in the table, construct a scatter plot that would be useful for showing the effect of water temperature on the ability of the devices to work for at least 5,000 hours, and comment on any trend or pattern that is revealed by the scatter plot you constructed. All right, let's see how you do. See what you can do. So here, remember that you have to have two variables that are quantitative. If you do not have quantitative, you cannot make your scatter plot. So you had to create a new variable p that indicates the proportion number of working over number of tested. And that's what you're going to put on the y. So you get to keep your temperature, that's definitely quantitative, and then you can use your proportion for your y. So this scatter plot looks very strong negative linear association between the temperature and the proportion of working devices at the end of the 5,000 hours. So you can see as the temperature increases, the proportion of working devices decreases. All right, oops. I think I hit it one too many times. All right, so find the least squares regression line and graph it on the scatter plot. All right, so we'll do that now. Let's go back. So go to your list, stat, edit, clear out your list 1 and list 2, and let's put it in. So in list 1 we have 10, 30, 50, and 70. All right, in list 2, I'm going to put the 29 out of 30. I got to go back to see the rest. So 29 out of 30, then 42 out of 50, 21 out of 30, and 12 divided by 20. All right, so let me go forward again. So now that I have that into my list 1 and list 2, I'm going to go stat and go over to edit and then go down to number 8, which is your linear regression, a plus bx, hit enter. Since you put them in list 1 and list 2, you don't have to put anything behind it. If you put them into different lists, you're going to have to put those behind it. And this tells me that y hat equals 1.02 minus 0.0062x. So there's my regression. And then it gave me an r value. It tells me my r is negative 0.9979. If you didn't get an R value, it's because you didn't turn your diagnostics on at the beginning of the module. And just call or email me if you still need help with that. So this R value is very close to -1, which again shows me the strength. Okay? All right, a residual. In most cases, no line will pass through all of the points in the scatter plot. So a good regression line makes the distances from the actual points that you have on your scatter plot to that predicted line as small as possible. So a residual means that the observed minus the predicted. And I remember this as actual data minus the predicted. And the way I always remember this is you are taking AP statistics. So actual minus predicted, AP for the residual. That's my mnemonic device. So to find the residual, you would take the actual data minus the predicted data. And in this case, we can see it's going to be negative. Here, if I did the sky, the actual minus the predicted, I can see my residual is positive. So basically what you're trying to do when you find this regression line, what your calculator does is it minimizes those distances as much as possible. So the least squares regression line, so they find the difference between the actual and the predicted, the actual minus the predicted, and they actually make it into a little square. So they have that residual and they make it into a square, and you're minimizing the sum of all of that area. Okay, so you're minimizing the sum of the squared residuals. So technology does this a lot easier than what we can, and that's why we use it. Okay, so in the least squares regression line, you have a couple other formulas that are very beneficial. This one right here is on your formula sheet. B, we know, is the slope. Okay. R is that correlation coefficient. S sub y is the standard deviation of the y's. And S sub x is the standard deviation of the x's. So if you knew some of the variables, you could plug them in and solve for the remaining. And then if you wanted the y-intercept, you could just rearrange that formula. This isn't too tricky. All right, so let's use this formula B equals R of S sub y over S sub x. The slope of the regression equals 1/2. The standard deviation of the explanatory variable is 0.2. The standard deviation of the response variable is 0.3. What is the correlation coefficient? So let's plug everything in. If the slope of the regression equation is 1/2, that's my B. I do not know the correlation coefficient, my R. Let's see. The slope of the explanatory, that's my X, is 0.2. And the slope of the response is my Y, is 0.3. Now I can solve for R. Sorry about that, but I got an R to be 1/3. Okay, the correlation coefficient is 9. The standard deviation of the explanatory variables is 2. The standard deviation of the response variables is 3.3. And what is the slope of the line? So you can just plug that in and get 0.135. All right. In Professor Friedman's economic course, the correlation between students' total scores prior to the final exam and their final examination scores is R equals 0.6. The pre-exam totals for all students in the course have a mean of 280 and a standard deviation of 30. Okay, so let's see, I know this so far, I know this, and that's important. The final exam scores have a mean of 75 and a standard deviation of 8. So that's for final exam, that's for the pre-exam. Professor Friedman has lost Julie's final exam, but knows that her total before the exam was 300. he decides to predict her final exam score from her pre-exam total. Find an equation for the appropriate least squares regression line for the Professor Friedman's prediction. Interpret the slope of this line in context of the problem. See how you do. Then use the regression line to predict Julie's final exam score. Julie doesn't think this method accurately predicts how well she did on the exam. Why? All right, so here we can find our B by plugging in what our standard deviation of our y is going to be, our standard deviation of the x's would be, and the r, the correlation coefficient. So if you remember, well, first off, what's your explanatory and what's your response? So your x in this case is going to be your pre-exam. Let's make sure we get that. And our y is going to be our final exam. All right, so here I can see that the pre-exam standard deviation is 30, and the final exam standard deviation is 8. So that's why I could put the standard deviation of the y over the standard deviation of the x. Then I can find my a. So I could use, I know that the mean x and the mean y is always going to be on my equation of my line. So using the mean x and the mean y that were given, so remember it said the mean of the final was 75, oops, that's y. The mean of the pre was 280. So I know that has to be a point on the graph. So I plug that in, plug my slope in that we just found, and I can see A is 30.2. So here I have my predicted final would be 30.2 plus 0.16, my pre-final. So if I want to find Julie's, I'm going to plug in her pre into this equation, and she got out a 78.2. Why does she disagree with this? Well, the correlation coefficient is 0.6, so that's not very strong. It's not weak, but it's not really strong. So I would say she definitely should fight the professor on that. All right, residual plots. One of the first principles of data analysis is to look for an overall pattern and for striking departures from the pattern. A regression line describes the overall pattern of a linear relationship between two variables. So we can see departures from this pattern by looking at the residuals. So residual plot, you keep the x exactly the same as you had in your regression, so that scatter plot from the original. And then the residuals go on the y-axis. So if this was my data, I'm going to keep the x's exactly the same. On my residuals, I know that they're going to be close around 0 because that's the whole thing. I tried to minimize the residuals. So I put 0 here in the middle, and I can label residuals, and I'm going to go a little bit below and a little bit above 0. So in this case, you could say, well, that one is about, 0.4, 0.3, 0.5-ish. So here my residual is going to be up about 0.4. This guy's distance is almost measurable, so and then this guy's is negative, so you're going to go down the same amount, etc., etc., for finding all of these. Okay? And that's how you make a residual plot. Now, when you look at the residual plot, your hope is that there is no pattern. No pattern is good. It means that you found a good best fit line to begin with. If there's a pattern, then the line of best fit would not be appropriate. Okay, so no pattern is good. So use the scatter plot to make a rough sketch of the residual plot for this data. So see what you can do. Here's mine that I made. So I started out with my x's being exactly the same. My y's become the residuals now. And in this case, I think I see a pattern. So I would say that this is not a good fit. There's going to be a better fit out there. Whether it be an exponential regression, a linear regression, it's not a good fit. So again, you want to make sure there's no pattern in the residuals, and you usually want them to be fairly small in size, meaning that they're close. So if I saw this as a residual plot, I would say that's very bad. Okay, a linear model would not be appropriate. All right, so how to make a residual plot on your TI-84. So set up the plot of the residuals against the X data. So put those in. Then you can go to your stat plot and hit enter. And what you're going to do is list 1, and then in the Y you're going to use resid. Okay. Now you can only do this after you've already found the linear equation. So you must have found your y hat equals a plus bx first. Okay? After you do that, so you'd already put all that in your list 1, list 2, that's when you're going to go do this step over here. Now go look at the plot for this new L1 resid. Don't worry about plot 1. And this gives you your residual plot. From here, you can see if there's any patterns. Okay. If you want more help with that, please click on this link or put it in you can go on the notes online and find it, or you can just type it in from there. All right, so is a linear regression the best fit for this data? So the first thing I did was I made a scatter plot. I did my linear regression. I found an R value of 0.9976, and I said, sweet, that's strong. That looks great. But then I did my residual plot, and I said, oh man, there is a pattern. So even though that R value was strong, there's actually something out there that's better than a linear regression for this data. R squared. R squared is your coefficient of determination. So remember, just a little recap, R is the coefficient, what did I just say? Correlation coefficient. And R squared is the coefficient of determination. So you kind of want to know this word for word. It will help you out if you just kind of state it in context of the problem exactly like this. So the coefficient of determination is the fraction or percent, so you could pick either one of those, of the variation in the y values. And again, y values put in context, whatever your y value is in that situation, is accounted for by the least squares regression line of y on x. And make sure you write these in context of the problem going on. Now, remember, association does not imply causation. So even though we're finding an association between these variables, it doesn't mean one causes the other. All right, for the least squares regression of fat gain on any A, our R squared was 0.606. Which of the following gives a correct interpretation of this value in context? So look through these. The correct answer is C. Okay, try this one. A recent study discovered that the correlation between the age at which an infant first speaks and the child's score on an IQ test given upon entering elementary school is 0.68, negative 0.68. A scatter plot of the data shows a linear form, which the following statements about this finding is correct. Sorry, I think that's just supposed to be positive. Like I think it was like a dash, but it's 0.68. So read through these. You can pause me, and you should get D. All right, interpreting computer regression outputs. Hang in there, you're doing great. The number of statistical software packages produces similar regression output. So on the AP test, they'll always have like these little outputs, and you want to be able to make sure you can find right now the slope, the y-intercept, and know the values of s and r squared. So for instance, this is what will show up a lot on the AP test. It's called a Minitab. So they're going to have this coefficient, SE coefficient, T, P, S, R squared, and sometimes they may have more, but those are what they're going to have a lot. For now, you don't have to worry about those. We're going to learn what those are later. This guy right here, you never ever want to use. Okay? So these will be later. All right, so now you're going to have the constant and the NEA change. This guy is going to be your x, this guy is going to be your y. So when you have this, this is your slope right here with the x, and this is your y-intercept, the constant. So I'm going to have y hat equals 3.5051 minus 0.003445 x. And you have to be able to write that. Okay, this guy right here is going to be the standard deviation for the constant. So the standard deviation for the y-intercept. This is your standard deviation for slope. This S is your standard deviation for the residuals. And this is the R squared you want to use. Okay. All right, the distinction between explanatory and response variables is really important in a regression line. Just kind of throwing some stuff up. So if you switched them, you get some different outputs. Correlation and regression lines describe only linear relationships. You're not resistant to outliers. An outlier we've talked about. An observation is influential for a statistical calculation if removing it would mark change in the result of a calculation. Outliers are often influential, but so could other points. Association does not imply causation. So here, a serious study once found that people with 2 cars live longer than people who own 1 car. Owning 3 cars is even better, and so on. So does that mean that these are, is this the cause? If you own more cars, will you live longer? No, it probably means that you have more money for health care and different things that make your life easier. So, and I'll let you look through all of these just to remember. Feel free to pause if I'm going too fast. And one more question. Let's see how you do on this. This is from the 2011 AP Statistics Free Response. So here you can see the computer output. I want you to write the least squares regression line, identify all your variables. How much more electricity would the windmill be expected to produce on a day when the velocity is 25 than on the day when the wind is 15? Show your work. What proportion of the variation electricity produced is explained by its linear relationship with wind velocity? And is there statistically convincing evidence that electricity production by the windmill is related to wind velocity? Explain. See how you can do on this. Okay, part A, predicted electronic production. If you had y hat, you needed to say y hat equals predicted electronic production. And then you can see the rest of this equation. So the slope is 0.240, which indicates that for each additional miles per hour of wind speed, the expected electricity production increases by 0.240. So if I wanted to see where I'm at, thus the expected electricity production is 10 times your 0.240, which is 2.4 amperes higher on a day with 25 miles per hour wind as compared to with the 15, because you went 25 minus 15 is 10. Okay. Part C, the proportion of variation in electricity production that is explained by the linear relationship is the R squared value, and it says that the R squared value is this. And D, you can do a little bit more with hypothesis testing. If you want to kind of look through that now, we will definitely be getting into that later, so you don't really have to worry about Part D. If you think you had a good explanation, that's cool, but we'll get to that later. All right, so your summary. Lots of stuff in this second section, right? Congratulations for making it through it. And I'll see you in the next module.